geometry, section 3.5. We'll get to that in just a moment. First, I want to show you the proof of the triangle angle sum theorem. This was what I had planned to show in class before we decided to go virtual this week. I do want you to see it. Not only is it important to prove these things sometimes just for quality and for reliability of the information that I'm telling you, that I'm not just telling you and you're taking my word for it, but also it's another good look at a proof. And once we prove it, then it is, of course, a theorem. So I have it mostly filled out anyway. Basically, you have a triangle here, and then you have a line that is parallel to this line segment, okay? And one quick adjustment that I make to the prove line, if you looked at the theorem in the book, it would say the measure of angle A plus the measure of angle B plus the measure of angle C equals 180. Well, the measure of angle C here is ambiguous because of that line being there. So I've gone ahead and numbered these three angles in here and replaced angle C with angle 3. So our goal will be to prove that the measure of angle A plus the measure of angle B plus the measure of angle 3 equals 180. Okay, so I went ahead and I wrote the given, and I said given. We would know that the measure of angle 1, 2, and 3, the sum of them would be equal to 180. As you look here, because they form a straight angle. I have justified that step with definition of a straight angle. Now, many would say, well, why isn't a definition of supplementary? For the purposes of what we do in chapter 3 with the definition of supplementary, which is an abbreviation on your little sheet, that's fine. You could use that here. I would understand why someone would use that. Technically speaking, though, supplementary angles are 2 angles, not 3. Okay, now that's a small point and don't really need to worry about that, but this is a better justification than definition of supplementary angles because of that small point. Okay, but don't worry about it. This is the only time you're going to run into that anyway. Okay, so we know that these 3 angles would add up to 180 because they form a straight angle. Then I start looking, excuse me, also I should have marked my lines parallel. Then I start looking and I notice that angle A and angle 1 are alternate interior angles, okay? And we know that parallel lines implies that alternate interior angles are congruent. So I've shown angle 1 is congruent to angle A. In the same way, angle 2 would be congruent to angle B because they are alternate interior angles. And these parallel lines, which along with the transversal do form those 2 angles, they're on opposite sides of the transversal, they're interior, the parallel lines. So that is parallel lines implies alternate interior angles are congruent, okay? And then it's a simple substitution from there. I can replace 1 with A, I can replace 2 with B, right? I'm just taking this A and putting it here, this B and putting it here because we know they're equal to 1 and 2 respectively. And we can write the measure of angle A plus the measure of angle B plus the measure of angle 3 equals 180. That is a substitution. The substitution property. Okay? All right, now let's move on to the 3.5 lesson. If you need to pause and reflect on what we just did, that would be great. If you want to revisit this video later, great. A definition. Polygon. Polygon is a closed plane figure with 3 or more segments for sides. This is the book definition. We talked in chapter 2 about the importance of good definitions. And this is a good definition. Closed because something like this would not be a polygon. A plane figure because something that's not 2-dimensional. If it were 3-dimensional, that would not be a polygon. And 3 or more sides because, well, look at this list here and you'll see them. We know these words, a lot of them. Triangle, quadrilateral would mean 4 sides. A pentagon is 5 sides. Hexagon is 6 sides, etc. These are the words that you should know. All of these words you should know, and would be fair for me to ask you on a quiz or a test about them, all right? If you want a little bit of advice here, these two get mixed up. Hexagon and octagon. They shouldn't, but they do. Octa, think of octopus. An octagon is like a stop sign that has the 8 sides because an octopus has 8 tentacles, where hexagon is 6. I think of like a hex nut that I have in my garage right now. A lot of your nuts that go on bolts have 6 sides. So don't confuse those two. Decagon and dodecagon, those are important also. If we get beyond 12, and I see we have none for 11. You can see we don't have one for 7. It exists, but it's not as important as the rest of these, so it's not in the table. If we get beyond 12, or if it's even an 11-sided figure or a 7-sided figure, just use that number dash gon. Okay, a 15-sided figure would be a 15 gon, 15 with a hyphen and then GON. Okay, and then also notice on this figure here that I just thought it was good to. I took a picture with this and of this with my phone, and I added it to my slide here. And since convex and concave are right next to it, I thought I'd just talk about them here too. This figure is what's known as convex. This figure is what's known as concave. The easy way to remember this is the cave part of this. It's kind of caved in here. It's like it's dented in. You don't see anything like that here. Okay. Now, a different way to define that would just simply say that it has an angle that's more than 180 degrees, as in an interior angle of more than 180 degrees. That's what you'd see right here. This angle right here is more than 180 degrees. Now, those two definitions are actually not the book definition. The book definition, in case you needed three, would actually show that if you draw from some vertex to another vertex and the line segment lies outside of the polygon, it's concave. Okay, so really any of those three definitions work. You don't need to know all three. You really should just grasp onto one. It's dented in, it has an angle of more than 180 degrees interior, or the book definition of the line segment lying outside. All right, so a couple of examples here. Name the polygon, then identify its vertices, sides, and angles. Identify its vertices would be the 5 letters. Its angles would be the 5 letters with the angle symbol, and the sides would just be the segments. So segment AB, segment BC, etc. I'm just going to show you the answer here and move on to the next problem. Pause it if you need to. Speaking of convex and concave, here we have a figure. It says classify the polygon below by its sides. All right, so if I start here and I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, when I'm back to the vertex where I started. So this is a dodecagon. 12-sided figure is called a dodecagon. And it's concave, right? It's caved in, it's dented in here. Now look again as they show you, they'll show that segment outside. Right, so there's the book reason why, because you can draw from one to another. And of course, that's not the only place. You could draw here or here, right? And the segment is lying outside of the figure, so that means it's concave. Again, also because this angle is clearly more than 180 degrees. Any of the three definitions there work. Okay, so consider these three figures. And we know already that the angle sum of a triangle is 180 degrees. The question is, what about a quadrilateral, 4 sides? What about a pentagon, 5 sides? What if we kept going? Well, here's an easy way to demonstrate why a quadrilateral has 360 degrees for a measure, angle sum that is. Because if I draw a segment like this, you'd have a triangle here that has an angle sum of 180. You'd have a triangle here that we know has an angle sum of 180. If I consider all the angles of the triangles, all 6 of them, that would incorporate all of the angles of the quadrilateral. So this would have an angle sum of 360. If I went to this pentagon and I drew like this, you'd have 3 triangles, 180, 180, and 180. That would be 540. And yes, the pattern continues. So notice this, that the number of sides, now let's say it this way, the number of triangles that you can create in this way always start at the same vertex. The number of triangles always lags behind the number of sides by 2. If you drew a hexagon, 6 sides, you'd be able to make 4 triangles. If you drew a 7-sided figure, you'd have 5 triangles. 8-sided figure, 6 triangles. So it's always lagging by 2. Therefore, the polygon angle sum theorem simply is n being the number of sides, take n minus 2 and multiply that by 180. Again, n is the number of sides. So if I said, for an octagon, find the angle sum of an octagon, it would be 8 minus 2 times 180, or 6 times 180. Note the parentheses mean you need to do the subtraction first, then multiply by 180. All right, back to 2 more examples. Find the sum of the measures of the angles of a dodecagon. Dodecagon has 12 sides, so that calculation would be n minus 2 times 180. That would be 10 times 180, which is 1,800. Now, don't immediately jump to thinking that, okay, now we can take that number and divide it by the number of sides to get the angle measure. That would be true for a polygon that has all the angles the same measure. Remember that word is equiangular. But that's not necessarily true. Again, if you think of the pentagon that I had drawn on the previous slide, all the sides were not the same measure. All the angles were not the same measure. So we'll get to that word in just a second about what it means to be all the same sides, the same measure, all the sides the same measure, and all the angles the same measure. But don't jump to that. All they asked for was the sum. It's 1800 degrees. All right. I beg your pardon. I misread that, and I'm not going to retake this video, so I beg your pardon. That doesn't say dodecagon, that says decagon. So the calculation would be 10 minus 2 times 180, which is 8 times 180, which is 1440. Please forgive. But now you know what it is for a dodecagon and a decagon. All right, another example. Note the right angle block here, 100-degree angle here. That means these have a sum of 190, okay? And then these angles, note they're being marked congruent. I don't know what they're doing with that tick mark there. They really could have just left that out. But no matter what they do, they put quadruple arc marks. If they were the same, they're of equal measure. They are congruent angles. So basically, you have two angles. Let's just call this N. You have two angles that are the same measure, plus 100, plus 90, and they're going to add up to the angle sum of a quadrilateral, which we just determined is 360. So simply solve this algebra problem. You'd get 2n. If you subtracted the 100 and the 90 from both sides, you'd have 170. So n is going to be equal to 85. Each of those angles, the measure of angle x and the measure of angle y, is 85 degrees. Now I'm going to do it like this. The measure of angle x is equal to the measure of angle y is equal to 85 degrees. 85. Okay, just about to wrap it up here. So with more time, I would demonstrate this for you. If you want to, you could do a little experiment yourself. Just draw a triangle and just pick some angle measures that add up to 180. You know, maybe this is 55 degrees and this is 68 degrees, and then subtract those from 180 and you come up with this angle. Do the same thing with a quadrilateral, make sure they add up to 360. Do the same thing with a pentagon, make sure they add up to 540, and keep going if you want to. And then draw an exterior angle, one at each vertex. Draw an exterior angle, one at each vertex. And using supplementary then, you could find out what each of those measures are and add them up. They will always add up to 360. That's a little surprising, but it's true. Okay, so again, take my word for it, or do a little 2-minute experiment if you want to, and you could prove it to yourself. Finally, it is true that the words equiangular and equilateral apply not only to triangles, but also to other polygons. Okay, now if it's an equilateral triangle, we did figure that the angles are all 60 degrees. That's of course going to be something different with each polygon that we figure. Anyway, if a polygon is both equilateral and equiangular, all of its sides are the same measure, all of its angles are the same measure, then we have what's called regular. That is a regular polygon. We don't say regular triangle because we have a word for that, and it's called equilateral, which happens to also then be equiangular. But once you get above 3 sides, 4 sides, 5 sides, 6 sides, that is, we're going to call it regular. Now, a regular quadrilateral also has a name, right? We call that a square. But then there's regular pentagon, regular hexagon, regular octagon, etc. Okay? The last example on the slide is kind of dumb, so I'm going to skip it and end the video here. Thanks for watching. If you want to see an example file, you can look in your textbook before you start the homework. Thanks for tuning in.